In section 4.3, we're going to be introduced to what is called the multiplication rule, and then the concept of what is called conditional probability. Now, both of these things are needing to be understood in the context of what are called independent events, or really understanding what is the difference between events that are independent of each other and events that are dependent on each other. So it says two events A and B are independent events if the fact that A occurs does not affect the probability of B occurring. Well, here's an example of that. Let's say we have a six-sided die, right? Okay, and we roll that dice. Now on our first roll, okay, that's event A. Let's say we roll a 4. And our second roll, so that's event B, let's say we roll a 3. Now, here's the question. Did me rolling a 4 have an impact on what was going to be rolled the second time? Well, no. Every time you roll a dice, it kind of resets itself in a way. And that every time you roll a dice, there's an equally likely chance of each event occurring. Okay? But let's maybe think about an example where it's sometimes good to see where things aren't independent of each other in order to really drill home the independence piece. So let's maybe think about a scenario. Let's say I have a group of people, and 5 of them are male and 5 of them are female. Okay. And let's say that I'm just randomly selecting people out of this group to be on my team. And let's see, I need to pick 2 people to be on my team. So, I'm going to randomly select it. I'm not going to do anything but randomly select who's going to be on the team. So what is the probability, okay, that my first person that I select is a male? Well, that would be 5 out of 10, or there's a 50% chance, right? So the first person, that's event A. Well, let's look at the second person that we select. Okay, what is the probability that I select another male for my group? Now we have to be careful. One male has already been selected. So how many males are left? There's only 4 males left out of how many people left? Well, I had 10, but I already picked a person. So there's only 9 people left to randomly select from. 4 out of 9. That's actually around 44%. What just happened? The probability of me selecting a male on my second turn was impacted by the probability, or is impacted by what happened in event A, my first event. These would be scenarios that are dependent upon each other. Okay? The reason these are dependent is we're dealing with something called non-replacement. Up here, when I rolled a 4, I essentially replaced the 4. I gave the 4 back to the dice to roll again, right? Here, when I select that first person to be on my team, that person's not back in the pool of people to select anymore. So that completely changes my sample space, and it changes the number of options in the specific outcome that I'm looking for. So that's the concept of independence and dependence when it comes to 2 events. Let's see how that applies here to what's called the multiplication rule. So it says this, when 2 events are independent, okay, so that's key. When they are independent, we have a formula for what's called the multiplication rule. So when 2 events are independent, the probability of both occurring is, notice our notation here, what's the probability of A and B occurring? Well, it's the probability of A times the probability of B. So if the multiplication rule addresses the scenario, what if I want two different things to occur at the same time? What if I want A and B to occur? Okay, let's take a look at this. Example, our first example here, tossing a coin. A coin is flipped and a die is rolled. Find the probability of getting a head on the coin and a 4 on the die. Okay, so I'm performing two different actions and I want a very specific outcome from each of those. What is the probability that I get both of those outcomes? Well, let's let A equal getting a head, and let's let B equal rolling a 4. Well, the probability of A and B, the probability of getting a head and rolling a 4, equals the probability of A times the probability of B. Well, what is the probability of A? Well, A is, right, getting a head. Well, flipping a coin, we know there's two sides, and a head is one of those sides. So the probability of getting a head is 1/2, 1/2. What about the probability of B? Rolling a 4. Well, how many 4s are there on a dice? There's 1 4. Out of how many possible outcomes? Out of 6 possible outcomes. So the probability of rolling a 4 is 1/6. Therefore, the probability of getting both of those to happen, probability of A and B, is equal to my 1/2 times my 1/6, which equals, remember with multiplication, straight across the top, 1 times 1 is 1, 2 times 6 is 12. So there's a 1 out of 12 chance that if I flip a coin and roll a die, I will get a head on the coin and I will get a 4 on the die. Let's look at another example. A card is drawn from a deck and replaced. Oh, there's that key word, replaced, meaning it's put back, it's reset. Then a second card is drawn. Find the probability of getting a king and then a 7. So let's let A equal king, and let's let B equal 7. We're interested in the probability of getting an A and a B, a king and a 7. Well, we know that that's the probability of A times the probability of B, if those two events are independent of each other. And they are independent of each other because of replacement. Meaning when I draw that first card out and I see what it is, if I don't put that card back in, that affects the probability of any other card getting drawn. But if I put that card back in the deck, I'm resetting everything back to its original probability. So we're good. What is the probability of getting a king? Well, I know that there's 4 kings out of 52 cards, so 4/52. What's the probability of getting a 7? Well, I know that there's 4 7s in my deck out of 52. And I believe these actually reduce to 1/13 and 1/13. That'll help us a little bit with the math, working with smaller or reduced fractions. Great. So what's the probability of A and B? It equals the probability of A, which is 1/13, times the probability of B, which is 1/13 as well. What does 1/13 times 1/13 equal? Let's see if we can get our calculator up here. Sorry for that delay. Calculator doesn't seem to be working on the computer, so we'll just do it old-fashioned way on a regular calculator. So we're going to do straight across the top, 1 times 1 is 1, and then straight across the bottom, 13 times 13 is 169. So there's a 1 out of 169% or chance of getting a king on your first draw and a 7 on your second draw. If I do that math, 1 divided by 169, I end up with 0.006. It's a pretty small probability because as a percentage, that's 0.6% chance. So there's less than a 1% chance that if I draw one card, it's a king, and then I draw another card and it's a 7. Very good. Well, let's look at this a little bit more, just to really drill this multiplication rule home. It says this: an urn contains 2 red, 5 blue, and 3 white balls. Now I'm going to stop there for a second. I'm going to add that up, and I'm going to say that there's 12 balls total in that urn. That's going to be important to us for probability. A ball is selected and its color is noted. Then it's replaced. A second ball is selected and its color is noted. Okay, find the probability of each of these events. Right? So we're selecting a ball, putting it back, selecting a ball, putting it back, selecting a ball, putting it back as many times as what each of these examples is asking for. So example A is selecting 3 blue balls. So here's the significance of this. The multiplication rule, notice here, it's actually asking for 3 blue balls. So what is the probability of, let's just say B equals getting a blue ball? What is the probability of getting a blue ball and another blue ball and another blue ball? In other words, what this example is illustrating is the multiplication rule isn't just good for 2 events occurring at the same, both occurring. It's good for multiple events all occurring that you desire. So this is just going to be the probability of a blue times the probability of blue again times the probability of blue again. We follow the same pattern in our formula. Well, what is the probability of getting a blue? Well, how many blue balls are there? There's 5. And some of you probably noticed I did my math wrong up here. 2 times 5 times 3 is not 12. 2 times 5 times 3 is 10. Okay, so 5 blue balls out of 10 total balls. Well, that just equals 1/2. So now I can finish this out. What's the probability of getting 3 blue balls? It's 1/2 times 1/2 times 1/2. Multiply straight across the top, I get a 1. Straight across the bottom, 2 times 2 is 4, times 2 is 8. As a decimal, that's 0.125. As a percentage, that's 12.5%. So we know that there is a 12.5% chance that if I'm replacing the ball each time I draw it out of the urn, that I get 3 blue balls in a row. Let's do part B. What about selecting 1 white ball and then a red ball? Okay, so what's the probability of, let's let W equal getting a white ball and R equals getting a red ball. So what's the probability of W and R? Yeah, it equals the probability of W times the probability of R. What is the probability of W? Well, how many white balls are there? There's 3 white balls out of our total 10. But we replace times, what's the probability of red? Well, there's 2 red balls out of, again, a total of 10. Multiplying those together, 3 times 2 is 6. 10 times 10 is 100. That equals 0.06, which is 6%. So there's a 6% chance that I select 1 white ball and then I select a red ball. Great. We're going to move on and not take a look at that third one. Those first two illustrate the point well. Great. Okay. Well, we've addressed the idea of what's the scenario, what is the multiplication rule when events are independent. However, okay, what about when things are dependent? When the outcome or occurrence of the first event affects the outcome or occurrence of the second event in such a way that the probability is changed, the events are said to be dependent events. Okay? Now, dependent events most of the time the examples that we're going to see are examples where things are not replaced, or when the first thing is selected, that is removed from my sample space, so that the probability of the rest of the items left in my sample space have all changed. Okay? So conditional probability, here's some notation for it. Okay? The probability of B given A. Okay, so this is the probability of B given A. That's how we say this notation right here. It's the probability of B given A. In other words, it's what it's asking is, or what it's communicating is, what is the probability of B happening given that A has already happened. In other words, something has already happened that has an impact on my probability of event B. Right? So it's recognizing that something has happened that has impacted the probability of B. Okay? So here is now our multiplication rule when we have two dependent events. When two events are dependent, the probability of both occurring is, notice we're still the same here, what is the probability of A and B occurring? Well, it equals the probability of A, nothing's changed there, times the probability of B given A. So in other words, all this is doing is it's saying, instead of just doing probability of A times the probability of B, it's saying we need to do the probability of A times the probability of B after having been impacted by A already occurring. Okay? Let's take a look at a few simple examples, and then we'll take a look at some more examples that really draw out this concept. It says this: for a specific year, 5.2% of U.S. workers were unemployed. Okay? During this time, notice this phrasing here, 33% of those who were unemployed received unemployment benefits. Can you see in that phrasing how conditional probability is being communicated? It's not saying that 33% of people received unemployment. It says, if you are unemployed, what's the probability that you received unemployment? 33%. Okay? 33% of those who were already unemployed, right? So it's not looking at all workers anymore. This percentage right here is dependent upon you being unemployed. It then communicates, if you're unemployed, what's the probability that you received unemployment benefits? 33%. Okay? So you can see in the wording the whole concept of conditional probability. Okay? If a person is selected at random, find the probability that she or he received unemployment benefits if the person is unemployed. Haha, you hear that? Okay, what is the probability that they received benefits if the person is unemployed? Right? In other words, what is the probability of A and B, where A equals unemployed and B equals unemployment benefits? But I know that these two are dependent upon each other. So really, this one here is, what is the probability of B given that A has already happened? All right? So what's the probability of A and B? It equals the probability of A times the probability of B given that A has already happened. That's the whole if the person is already unemployed. Okay, so what's the probability that they received unemployment benefits, B, given that they already are unemployed? That's the A. Well, for us in this example, there's not a lot to figure in that those percentages were given straight to us. Now, when we're working the multiplication rule, we don't want to work in percentages. You always want to work in fractions or decimals. So what is the probability of A not being unemployed? It's 5.2%. So 5.2% as a decimal is 0.052 times, what's the probability that they received unemployment given that they were unemployed? Well, 33%. That's 0.33. Okay. Now, taking a look at that, if we go 0.052 times 0.33, I end up with 0.017, which as a percentage is 1.7%. So there's a 1.7% chance that a person received unemployment benefits if they were actually unemployed. Very good. Let's continue taking a look at how this plays itself out and how we see it in different contexts. This whole idea of conditional probability worked into the multiplication rule. Selecting colored balls. It says box 1 contains 2 red balls and 1 blue ball. Box 2 contains 3 blue balls and 1 red ball. A coin is tossed. If it falls heads up, box 1 is selected and a ball is drawn. If it falls tails up, box 2 is selected and a ball is drawn. Find the probability of selecting a red ball. So we've got a unique scenario here where the first thing that occurs is we flip a coin. But then that coin then determines which box we pick. And each box contains a different sample space size and a different number of red balls. And so the probability of selecting a red ball is what? It's dependent upon the coin toss. Now, a tree diagram is often a really good way of viewing what's happening here. Okay, so the first thing that happens is I flip a coin, and when I flip that coin, I either get a heads or I get a tails. Great. What is the probability of getting a heads? Well, we know that's 1/2. What's the probability of getting a tail? 1/2. Great. So getting a heads does what? If it falls heads up, that means I'm at box 1. Now, box 1 has 2 different outcomes to it. Box 1 contains 2 red balls and 1 blue ball. So I'm going to go red right here and blue right here. Well, what's the probability of getting a red? Well, there's 2 red balls and 1 blue ball. So that means red, there's 2 out of the 3 balls. So there's a 2 out of 3. The probability is 2 out of 3 for getting a red. What's the probability for blue then? Well, there's 1 blue out of the 3. So we have that branch figured. What about this branch? When we get tails, we're asked to use box 2. Well, box 2 also has red and blue balls. Okay, it says that it has 3 blues and 1 red. So let's focus on red first. I have 1 red out of 4 total. So that's actually 1 out of 4. That's the probability of getting a red if I'm in box 2. What about blue? Okay. What about blue? Well, for blue, I know I have 3 blue balls out of the total 4 balls. Great. Here's what I want you to recognize. All of these probabilities right here are conditional probabilities. Okay. Here, this probability right here, there is a 2/3, 2 out of 3, which is 66 points, so it's about 67%. There's a 67% chance that you select a red ball given that you flipped the coin and got heads. Can you see the conditional part here? Whereas down here, there's a 1/4% chance, or not percent chance, there's a 1 out of 4 chance of getting a red given that you flipped the coin and got a tail. Okay? So all of these, like we just said, these are conditional probabilities. They are probabilities dependent upon something else already happening. But here's what I'm interested in. I'm not interested in finding the probability of a red ball given that something else has already happened. I'm interested in what's the probability of a red ball altogether. So the reason a tree diagram helps us with that is I can trace all of the lines in our tree diagram that result in a red and add those together to get the total probability of getting a red. So I have two different pathways. I have rolling ahead and selecting a red from box 1. Well, to find that probability, I go 1/2. What's the probability of a head and a red? It's 1/2 times 2/3. So 1/2 times 2/3 is equal to 2/6, which equals 1/3. Where's my other path? It's rolling a tail, getting to box 2, or rolling a tail, flipping a tail, getting to box 2, and then selecting a red. Well, the probability there is 1/2 times 1/4. That equals 1/8. Great. So those are the two different avenues of conditionally getting a red ball. In order to figure out the total probability for selecting a red, we actually go back to section 4.2, which was not the multiplication rule, but the addition rule. I want to either get a red this way, or I want to get a red this way. What's the probability of this or this happening? You add them together. So what is 1/3 plus 1/8? Addition, I need a common denominator. I think that common denominator is a 24. So I think this is going to be an 8 out of 24 is the same thing as 1/3, plus 3 out of 24 is the same thing as 1/8. So that is going to end up giving me 8, 9, 10, 11. I add across the top over my common denominator of 24. So 11 out of 24 is the probability of selecting a red ball. Now what we want to do is to kind of finish up this last piece of section 4.3 is we want to take a look at conditional probability a little bit more in depth. Okay? Now I've got a scenario here. Take a look at this formula. Every piece of it should look familiar. Go back to the second multiplication rule. The probability of A and B is equal to the probability of A times the probability of B given A. All I did to get from here to here was I divided both sides by the probability of A. Those go away. So what do I have? I have the probability of B, given that A has already happened, is the probability that A and B happen all over the probability of A. And that's what I have right here. So in other words, it's saying this. I'm not always given scenarios where it's easy to know what the probability of B is, given that A has already happened. In other words, the probability that this event has occurred, given that another event has already occurred. But all I had to do was rewrite the multiplication rule, and I now have a formula for conditional probability. It's what is the probability that both A and B occur divided by the probability of A. Let's take a look and see what this looks like in practice. We'll have two examples here to illustrate this. First example, a box contains black chips and white chips. A person selects 2 chips without replacement. Key word. If the probability of selecting a black chip and a white chip is 5 over 56, and the probability of selecting a black chip on the first draw is 3 over 8, find the probability of selecting the white chip on the second draw, given that the first chip selected was a black chip. So in other words, I'm finding what is the probability that I select a white chip given that the first chip selected was a black chip. Can you see that there? Find the probability of selecting the white chip excuse me, given that excuse me, that the black chip was already selected. Well, we have a formula for that. It's the probability excuse me, of a white chip and black chip all over the probability of black chip. Now, if we reread this problem, what's really nice is, if you'll notice, these two probabilities are given to us. It says the probability of selecting a black chip and a white chip is 15 over 56. That's this numerator right here, 15 over 56. Okay, let's bring that down here. So 15 over 56. And I have to divide that by the probability of B. What does it say here? The probability of selecting a black chip on the first draw is 3/8. So this is divided by 3/8. Now, I've got a division problem let me just erase that real quick. I've got a division problem of fractions. Well, I know I can do that by taking my first fraction, 15 over 56, and multiplying it by my denominator fraction, reciprocated, flipped over, the reciprocal of it. Great. Well, I see a few things that I can do. I can reduce 3 and 15, that's 1 and 5. And then I think 8 goes into 56 7 times. So that's a 1 and a 7. So what do I end up with? 5 times 1 is 5. 7 times 1 is 7. 5 over 7. If I do that real quick, 5 divided by 7, I end up with 0.714. So there's a 71.4% chance of selecting a white ball given that a black one was selected first. Let's take a look at another example. This example, I think, is a good example because it kind of puts it in perspective of the context that we're going to see conditional probability most often. It says a survey asked 100 people if they thought women in the armed forces should be permitted to participate in combat. The results of the survey are shown. Okay, so they asked people, and they recorded what their gender was, and they recorded whether they said yes or no. So in other words, what this is communicating is, of the 100 people that were asked, there were 32 males that said yes. There were 42 females that said no. Or there were 18 males that said no, or 8 females that said yes. So in other words, it took every person, each of these 100 people, and put them into 2 categories. It said, are you male, are you female, and did you say yes or did you say no? What's really nice about how this is set up is you also see what was the total number of males asked this question. Well, 50. What was the total number of females? 50. Well, what were the total number of people that said yes, women should see combat? 40. What were the total number of people that said no, women should not see combat? 60. Okay. So we have a really nice setup here that shows us how our data is distributed. Let's look at some conditional probability here related to this. Find these probabilities. Find the probability that the respondent answered yes, given that the respondent was a female. So here's how I'm going to write this. I want to know what is the probability that they answered yes, given that they were a female. Well, following the formula that we saw up there, that is the probability that they said yes, and what's the probability of yes and female all over the probability of female. See, all I did was take this up here, okay, and apply my own variables to it. Excuse me. So taking a look at that, we're actually going to adjust something really quick. Oh, nope, we're good. Never mind. Okay. So with this, how can I use this table right here to help with that? Okay. Well, what is the probability of yes and female? Here's the really nice thing about being able to look at it in a table. Which one of these numbers is both yes and female? Here's my yes column. Here's my female column. It's the 8 right here. So this top value up here is 8 out of 100. That's the probability of yes and female out of the 8 of them out of my total 100. But this is all divided by, given that it is a female. Well, how many females were there? There were 50 females out of the 100. So what's the probability of female? 50 over 100. Well, we have some fractions that we're dividing, so I can actually switch this into 8 over 100. Instead of divided by, it's now multiplied by 100 over 50. So this equals, you can see those cancel out nicely, 8 over 50. 8 over 50 reduces to 4 over 25, which equals 0.16 or 16%. So there's a 16% chance that a respondent answered yes, given that they were a female. Good. Let's look at the next one. The respondent was a male, given that the respondent answered no. So we want to find what's the probability that the respondent was a male, given that they said no. Well, that's the probability of M and N, male and no, all over the probability of no. So what's the probability of male and no? Well, my male row is here, the no column is here, there's my 18. So that's going to be 18 out of my total 100 people are men and said no. But I have to divide that by, given that they answered already no, right, for my conditional probability. So what's the probability of no? Well, 60 people said no out of the 100. So 60 over 100. Switching this to a multiplication problem, 18 over 100 times 100 over 60. The hundreds cancel, and I'm left with 18 over 60. 18 over 60 reduces to 9 over 30, and I believe that reduces yet again to 3 over 10. So that is a 0.3 or 30%. So there's a 30% chance that the respondent was a male, given that they responded no. So there's more context in which you'll see conditional probability at play. There's one more example we want to look at here in section 4.3 to wrap things up, and it's the probabilities for scenarios where it says, or where you're looking at a scenario of an at least. What do we mean by that? Look at this. It says this: a person selects 3 cards from an ordinary deck and replaces each card after it is drawn. Find the probability that the person will get at least 1 heart. At least 1 heart. So our event, H, we'll call it, is getting a heart. Now they're drawing 3 cards, and they want at least 1 heart. Here's the problem. There's a lot of different scenarios that you can get at least 1 heart. You could get no heart, 1 heart, right? You could get no heart, 1 heart, and then a no heart. All right, let's actually draw this out. You could get no heart. You could get heart, no. You could get no heart, no out of the 3 cards. You could get a heart, no heart, no heart, no heart. I could go on. There's several more scenarios. I don't want to find the probabilities for all of those different scenarios. I want to get rid of that. There's too much to figure out there. Okay. Here's the trick. Here's how we can approach this type of problem. Okay. A person selects 3 cards from an ordinary deck and replaces each card after it is drawn. Find the probability that the person will get at least 1 heart. It's going to be easier for us to find the exact opposite of what we're looking for rather than what we're actually looking for. But then there's something we can do at the end to find what we're actually looking for. So I'm going to say, remember the H bar? That's the complement. H bar is not a heart. Okay? What is the opposite of getting at least 1 heart? Well, the opposite of getting at least 1 heart is getting no heart. Okay, so I'm going to find H. There's only one option of getting no heart. It's first card, no heart, second card, no heart, third card, no heart. Okay, so whereas in finding the probability of getting at least 1 heart had a bunch of different outcomes, getting no hearts, it only has one possible way of achieving that. Okay, so what is the probability of no heart? 3 times. So no heart and no heart and no heart. Well, it's the probability of no heart times the probability of no heart again times the probability of no heart again. Well, what do we know that is? I know that there's 13 hearts out of the 52. So there's actually 39 cards that are not hearts out of the 52. Right? So 39 over 52. We are replacing. So the second time, there's again another 39 over 52 times the third card I draw. I don't want a heart again. That's another 39 over 52. So if I perform that mathematics, really what I have here is 39 over 52 cubed. So I'm going to, in my calculator, do 39 divided by 52, and I am going to cube that. And I end up with 0.422. Now, I just found the probability of no heart, but I didn't want that. I wanted the probability of at least 1 heart. Do you remember from the previous section where we saw that the probability of some event E is equal to 1 minus the probability of E complement. We can use that here. Instead of E, I have H. So what's the probability of actually getting at least one heart? It equals 1 minus the probability of not getting a heart. Now, in reality, this is heart, 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 and this is not heart, not heart, not heart. But what does that equal? It equals 1 minus my 0.422. So 1 minus my 0.422 ends up giving me a 0.578. So there's a 57.8% chance that if you draw 3 cards from a deck of cards, at least one of them will be a heart. So section 4.3, it's a big section, a lot of concepts in here related to the multiplication rule and conditional probability.